So you can think of kinematics and dynamics as a 5-act play. The first act, the introduction, that's where we learned about transformations, ways of representing both rotational and translational motion. Then in the second act, that's the build-up, that's where we discussed forward kinematics and inverse kinematics. Then the climax of our story is the differential kinematics. That's where we studied the Jacobian, how to derive it, and then use it. Act 4 is where we begin our discussion of dynamics with forces and torques. Here we use the transpose of the Jacobian. Now we're in the concluding act, Act 5, dynamics, equations of motion. Last time, we discussed the equations of motion of point masses. Today, since robots have rigid bodies that are not point masses, we're going to discuss the equations of motions for systems that have rigid bodies. Recall last time, we introduced the Lagrangian. The Lagrangian is simply the difference between kinetic energy and potential energy. It's a function of your generalized coordinates. So for an n degree of freedom system, you'll have n generalized coordinates. But it's a function of your generalized coordinates as well as its velocities. The way we derive the equations of motion is that we differentiate the Lagrangian with respect to each generalized coordinate velocity and differentiate that with respect to time, and then subtract from that the derivative of the Lagrangian with respect to that particular generalized coordinate. If you have n degrees of freedom, then there'll be n Lagrange's equations. The right side of Lagrange's equations you can think of as the input, or the torque input, the generalized torque input onto the jth degree of freedom. When you're done, you're going to have n coupled second-order differential equations. This means that the jth differential equation can have generalized coordinates from qi, where I is not equal to j, in other words, the other variables. The left side of Lagrange's equations will be a function of your generalized coordinates and their velocities, whereas the right side are the applied generalized torques, the applied generalized forces. Finally, in order to solve the differential equations, you're going to need two pieces of information. Here, we're going to use the initial configuration as well as the initial velocity of our system. Now, in this class, we're not going to require that you can go solve every possible differential equation, but as we discussed last time, we're going to give you the form of some solutions to differential equations and require that you can reason about it. At the very least, what we want to be able to do is have you be able to derive the equations of motion either for a point mass system or a system that contains rigid bodies. So now let's go to Lagrangian for the system that has rigid bodies. Lagrange's equations has the same form, except your kinetic energy is not only 1/2 mv squared, but you're also going to have a contribution due to the rotational kinetic energy. It'll be 1/2 moment of inertia angular velocity squared. Recall that the moment of inertia has this form here where you're given the mass density, how the mass in your system is distributed. What we're going to do in this class is we're going to assign moment of inertia as if it is a property just like mass is. If you think of mass as the resistance to translational motion, think of moment of inertia as a resistance to rotational motion. And just as we may give you m sub I, we're going to give you I sub I as well. Let's consider this example. It's a 2 degree of freedom robot. This robot has one rigid body here that has this revolute joint and center of mass located as such. And it has a second rigid body over here with its center of mass located there, except this rigid body is subject to motion through a prismatic joint. Now the masses of the two rigid bodies are m1 and m2 respectively. Likewise, the moments of inertia are just I1 and I2 respectively. In this system, it's a planar system. So for here, we'll assume that gravity is pointing down, and our workspace coordinates are x and y, or x1, x2, with gravity pointing down. Our generalized coordinates are q1 and q2. Here, q1 is the orientation of the first degree of freedom, theta 1, and then q2 is the displacement of the prismatic joint on the second rigid body, which is d2. In this example here, we're going to measure our rotational degree of freedom with respect to the horizontal, which is standard as we've been doing before. Our translational degree of freedom, we're just going to assume that 0 is over here. It's a little bit idealized, but that's okay. If you want, later on, you can have a statement that says Q2 can fall between some minimum distance and some maximum distance. But for this example, let's just say Q2 go from 0 to infinity. So when we start deriving Lagrange's equations, we begin by looking for the positions and velocities of the center of masses of the rigid bodies. The position of the center of mass of rigid body 1 is straightforward. The x position is cosine q1 times r1. The y position is sine q1 times r1. Straightforward trigonometry. We differentiate this position with respect to time, and we get the velocity of the center of mass of rigid body 1. Again, don't forget the chain rule. Likewise, the position of the center of mass of rigid body 2 is cosine theta q2 for the x position, and then sine q1 or sine theta times q2 for the y position of the center of mass. Once again, when we differentiate this, we get the velocity for the second link. Here, not only do you have to remember the chain rule, but also the multiplication rule, because both q2 and q1 are both functions of time. So here you can see this is the derivative of this guy times the first minus plus the first times the derivative of cosine, and that's where the minus sign comes into play. And similarly for the y velocity on the second rigid body. So with these two notions of velocity, what we're able to do now is take their dot product, because we're looking ahead for kinetic energy, and v1.v1 is this expression, and then v2.v2 has two contributions. It has this rotational part, which is similar to the velocity that you saw with v1, v2, but it also has a translational component, which this translational degree of freedom is contributing toward. But this is pretty straightforward to find using straightforward algebra. And now we'll compute the kinetic and potential energies of the system so we can derive Lagrange's equations. Just as a reminder, here are the v1.v1, the v2.v2. These are the translational velocity contributions to kinetic energy, but we also must consider the angular velocities. Omega 1 is simply q1 dot, and since the second rigid body and the first rigid body are along the same axis of rotation, its angular velocity is also going to be q1 dot. So let's look at the kinetic energy of rigid body 1. We have our 1/2 mv squared plus 1/2 I omega squared, and now simply substituting in, this is the form of the kinetic energy of the first rigid body. The kinetic energy of the second rigid body similarly follows. It's 1/2 mv squared, 1/2 I omega squared. We substitute in for v2.v2, we substitute in for omega 2, and this is the form of the kinetic energy of the second rigid body. The potential energies are also rather straightforward. All we have to do is worry about mass mgh of each of the centers of masses. So m1, this was the acceleration due to gravity, and then this is the height of the center of mass of rigid body 1. Likewise, m, acceleration due to gravity, and this is the height of the center of mass for rigid body number 2. So now we substitute in for T1, T2, V1, and V2. Remember, Lagrangian is T minus V, and we have this expression here. It's really important at this point that you start to be careful about how you do your substitutions. It's very easy to make a sign error, and I really implore you to take this nice methodical one step at a time. So that minus sign here, remember, it goes to the V1 and the V2. We're going to make a substitution of variables just to make this expression a little bit easier to follow with this gamma 1 and gamma 2. Gamma 1 is only going to be a function of Q2, and gamma 2 will also only be a function of Q2. Here, all we're doing is just showing a little bit of foresight and trying to be neat. You don't have to do this when deriving Lagrange's equations, but it's not a bad trick to see. And now we're going to derive the equations of motion using Lagrangian formulation. We wrote the Lagrangian over here just for your convenience. Remember this gamma 1 and gamma 2 substitution. And then here's Lagrange's equations. It's really important when you're working with Lagrange's equations to do things one step at a time. It's very, very easy to make a sign error and then get your system wrong. So first thing we're going to do is we'll differentiate with respect to Q1 dot, and we'll also do the differentiation with respect to Q. Over here, when we differentiate with respect to Q1 dot, this is the only term that has Q1 dot in it, so that's the gamma 1 Q1 dot. Then we differentiate this whole thing with respect to Q1. This is the only term that has a Q1 in it, so that's why we have the minus gamma 2 cosine Q1. Note that this minus sign comes from the formulation of Lagrange's equations, and this minus sign comes from what was present in the Lagrangian as we derived it. And now we'll evaluate this line. Remember, we have the multiplication rule, so this is the derivative of the first times the second, which is this term here, and then we have the first times the derivative of the second, and it's a little hard to see, but there really are two dots above this Q1, so this is Q1 double dot. Here, these two minus signs form the positive sign. Now, since we have expressions for gamma 1 and gamma 2 as functions of Q2, it's tempting to break apart this d gamma 1 dt using the chain rule. So this becomes d gamma 1 dq2 times dq2 dt, resulting in this expression here. Notice the second dot is more apparent in this expression. Now, since gamma 1 is a function of Q2, we're able to differentiate that with respect to Q2, and this is the resulting equation of motion associated with the first generalized coordinate. For the second generalized coordinate, we play the same game, and remember, we may have an opportunity to use the chain rule to break out a d gamma 2 dq when coming up with the second Lagrange's equations. So now let's look at the two equations together. It's worth noting that both equations have terms multiplied by an acceleration term. Again, that little dot is hard to see. And then they have quadratic terms in the first derivative. So there's a Q1 dot times Q2 dot as an example. And then finally, we have configuration-only terms. So before we go on, let's just talk about the torques, the inputs to these degrees of freedom. Normally, these torques, as prescribed in Lagrange's equations, is that they're applied directly onto the generalized coordinates. However, it'll often be the case that you can't apply a force or torque directly onto the generalized coordinate. For example, for this two-link system, let's say we want to be able to resist a force F1, F2 at the end effector. How do we map that force at the end effector onto the generalized coordinates? Well, we use the Jacobian. See how it's all starting to come together? So let's just review. Here's our 2-degree of freedom system, theta 1, d, Q1, Q2. The forward kinematic map is simply the position of this end effector as a function of Q1 and Q2. We had to introduce this little a in here on this slide just to get to the position from the center of mass to here. We then differentiate the forward kinematic map. That's what gives us our Jacobian. And the resulting Jacobian has this form, which I think should be somewhat familiar to you. Remember, a column of the Jacobian corresponds to the contribution of that corresponding degrees of freedom velocity to the end effector velocity. We can then get the generalized torques applied onto each of the degrees of freedom using the transpose of the Jacobian, and it has this form here, Jacobian transpose, and F1, F2, that's the force that the end effector is trying to resist. This will now be the torques that will be on the right-hand side of Lagrange's equations when we go to derive the equations of motion of the system.